We have Andrew Swartz here. He is the lead scientist at the UC Berkeley Central Sierra Snow Lab and has been researching winter weather, its trends, and its impacts for over a decade. So we're gonna dim the lights and make sure everybody's unmuted and we're good to go. All right, thank you. Let's give a warm welcome to Andrew.
Thanks, guys. Much appreciated. Thank you for joining me this evening. A little bit of a different crowd compared to when I teach at the university, so this is fantastic. More experience in the room for sure. So first things first, I want to say thank you for all coming out, but also, has anybody been able to hit that awesome snow this last week? How good is that, right? Super, super awesome. So I'm going to talk today about our snowpack, how it's changing, a little bit of how it's influencing our backcountry activities and the hazards that it can present. So, as I mentioned, snow is terrific. This picture I actually got at Sugar Bowl on Monday as we were getting in some good turns, which was fantastic. On the right-hand side of the screen, you can see the Central Sierra Snow Lab measurement site, kind of our crown jewel. And then on the left, you can see part of what I'm going to talk about that influences our snowpack. No. Okay, so spacebar? Also no. Clicker button doesn't work. Haha. So, I have always loved snow. This is me growing up in Denver, Colorado. You'll notice I am not sad in any of those pictures. I grew up absolutely stoked to be out in winter storms. I was constantly pretending I was in Antarctica. One of my favorite memories is actually when I was out completely snowing in the middle of December. We just gotten done with like a Christmas concert at my preschool. And my mom was like, you have to come inside. You have to come inside, get out of the snow. You're going to freeze. And I was like, no, she had to drag me in. So I have always loved this stuff. And that love has, even though there's been a few bumps between the way, I was in high school. I was like, school's terrible. I'm not doing this anymore. So I went and did some odds and ends jobs after I got out of high school. But that love remained. And eventually I found my path into doing it professionally. Button worked that time. Oh, it's way too far. Professionally. So my mid-20s, I went back to school for meteorology and atmospheric science and did some storm chasing, still one of my pastimes. I did a lot of work at the National Center for Atmospheric Research, where this is me acting like kind of a farmer with the grass in my mouth. I'm not a very serious person, so but made this wonderful career out of it. And again, can't help but smile in the snow, right? So this is terrific. And I've absolutely loved coming here and talking to you guys because I'm very passionate about this. I live at the Snow Lab, which is great because if I didn't, I'd still be staring out the window at snow anyway. So I did all this kind of throughout my career, weaving kind of this awkward path, and then decided I wanted to really direct research and understand the snowpack more. So I went to somewhere that everybody associates with snow, Australia. You know, kangaroos, the outback, and snow, right? But this is the Snowy Mountains for anybody that has the Epic Pass. There's Perisher Ski Resort down there, and that's where a lot of my research was done. So this actually produces about 66% of the fresh water for the most important river in Australia. Very important stuff. My research down there focused on how bushfires change the landscape and what that means for our snowpack and water. So kind of crazy, but that leads into some stuff that I'll talk about later. Aha. Who's up for a history lesson? I'm sure everybody was expecting that when they're like, we're going to learn about snow, right? So this is Thomas Edison with his invention of the phonograph. Well, technically that's the second iteration, but his invention of the phonograph. The same year, San Francisco installed their first ever telephone exchange. It serviced a whopping 18 lines, and people were still skeptical about whether or not the telephone was going to take off as a technology. That same year, the United Kingdom issued their first ever weekly weather forecast. This is not it. I tried to find pictures of it. You wouldn't believe how hard it is to find that, but it was something similar to this. Now you're probably all sitting there going, why are we talking about all these weird non-connected events? And that's because when we talk about Donner Summit, okay, when we talk about Donner Summit, go back one, come on. There we go. We had the Transcontinental Railroad, right? Oh, now we went too far. We'll get it one of these days, guys, I promise. So we had the Transcontinental Railroad, right? Well, all those other things that happened the same year. It was 1878. And the Transcontinental Railroad happened prior to that. But they started doing something very, very important that same year. And that was, you probably just saw it on a slide anyway, but they took the first measurements of snowfall and snowpack that were then recorded and used for data later on. So the reason I brought it up like this is because if I go, there we go. If I go, yes, we've been doing this for 150 years, it gets lost in translation a little bit. We hear a lot of numbers that are thrown around, but that 1878, it's all the way back here. And technically that's 1879 because it's the winter of 1878 and 1879. So those were the things going on when we first developed our records in the region. This was the first year, 1878 was the first year electricity was licensed to be put in houses or businesses. The first business ever installed light bulbs in Philadelphia that year. That's how long we've been doing measurements of snow in the Sierra Nevada. Not how long I've been doing it, luckily, but how long we've been doing it. Come the mid 20th century, the Central Sierra Snow Lab was created in 1946. This is an old picture on the left that you guys can see. It was called the Tea Kettle Cabin. It effectively has lab space on the first and second floors and living space up top. On the right, we have all of these notebooks through 2000, I think in 6, if I recall correctly, with handwritten records of weather every single day from beginning to when we started digitizing it, basically. Now, most of that's done on spreadsheets, but they're still kept. So we've been continuing these measurements since 1946. Now, you'll notice that the Snow Lab was not on a train track. And so comparing those early records to what we did at the Snow Lab and what we do at the Snow Lab is a little bit difficult. Cool. And this last storm can tell you a little bit, okay. And that last storm can tell you a little bit about why it's difficult to compare. There we go. Compare these records, right? Okay, thank you. So we have 3 places on the summit, Sugar Bowl, Boreal, and the Snow Lab this last snowstorm, and we see 55 inches, 60 inches, and 51 inches. No 2 places are the same, right? We've all been out on snow, we've seen drifts, things like that. So we can't really compare those records all that well. So what we have to do then is take these records and bifurcate them. We take everything on the right-hand side that the Snow Lab's done, and we take everything on the left-hand side that the railroad's done. And we can still use these records for comparison, but not directly. So what we tend to look at with those early records is how there's changes from season to season in our snowfall, whether things like El Nino impact it, variability from year to year, and really paying attention to what's going on. But again, that's in a different spot. So those records could be a couple feet off. Am I good to take questions in the middle, or we wait until the end? Yeah. Not really, no. There's proxies that we can use, things like coral samples and things like that tell us the history of temperatures out across the ocean. But that's getting into paleoclimate, not so much my area, but we're working on how it impacts the snow up top now that we do have measurements of it. So brings me to my next point. We can do some work with this, and it's an interesting piece of history. But this stuff on the right-hand side where the Snow Lab started, that's what's really important. So that time it worked, pointing at the screen. I don't know why I feel like I have to use it like a TV remote. So that's just one portion of our records, is that maximum snow depth and our snowfall overall. We also have manual observations. And again, these are, when I say manual, these are people going out in the snow and doing them themselves. They have thermometers, they have rulers, whatever it might be. So we have measurements from what we call water year, or WY, which is October 1st to September 30th. So effectively, you can think of it as the winter from 1945 to 1946. So from water year 1946 to present. Until recently, we only had the data available from 1971 forward. Thanks to the hard work of Sonia Quatra here, who is an undergraduate at UC Berkeley, we now have digitized records going all the way back to 1958. Those will be put online. And the cool thing about these records is, if you guys want to download them and take a poke at them, you can. They're really easy to understand and look at and play with on your own. So we have this amazing record as well. Maximum and minimum daily temperature, precipitation, snow characteristics, good stuff. One of my favorite things to talk about in terms of data and record is the USDA NRCS SNOTEL, which is a lot of acronym. It is the US Department of Agriculture, Natural Resources Conservation Service snow telemetry site that we have at the lab. USDA NRCS SNOTEL. And that's from 1980 to present. Now that's all automated observations. And you'll notice that there's a lot of overlap between the manual observations and the automated ones. And that's because, for one, these sites were deployed largely throughout the Western United States, and I'll show that in the next slide. But also because it takes a lot of effort to get people out continually to do these measurements. Not everyone has a snow lab, right? So we needed a way of automated them. And the nice thing is, we can take and compare these against each other. If we have a record that stops for any reason and we need to go back and look to see if it's accurate, we can easily compare them, right? So, as I mentioned, these sites are all over. One of these days I'll get it. There's a lag. These sites are all over the Western United States. We've got about 1,000 of them, which is really, really cool. And I promise I'm getting to the more sciencey backcountry bits as well, but we need to set it up this way for a specific reason. This is how we know everything that's been happening with our climate, with snowpacks. We have massive number of stations, 1,000 of them basically between the Western United States and Alaska. These goofy little ones that aren't filled in California, those are run by the California Department of Water Resources. So massive number of stations monitoring this stuff. And in addition to it, we are keeping an eye on all of our snowpack with new technologies as well, such as the Airborne Snow Observatory, which was part of a NASA JPL program that kind of, after it wrapped up its initial purpose, went rogue and is now continuing to do some amazing data collection and work. And then we have our wonderful GOES satellites down there on the bottom. Figured it out this time. So we have all these observations, but what story do we get from a climate perspective? What story do we get from a snowpack perspective? And what trends are there that we can examine? And this is where these long-term data sets are so very useful, because if we have 15 years, you can't really tell what's going on very well in terms of trends. Oh, didn't like me that time. Okay. So I've only been at this job for about 18 months. So far, I absolutely love it, but I wasn't all that familiar with a lot of the data that the Snow Lab had. And so I decided to take a look at some of this data for something called the Western Snow Conference, which was started, for any of you snow history buffs, by well, I shouldn't say it was started, but featured a lot of Dr. James Church's research that developed the Mountain Rose sampler, which we still use today to determine our snowpack. And when I got out here, there were a lot of people that said, there's a lot more rain on our snow. And that's something that I noticed in Australia as well. So I went, well, why don't we check out what's going on with rain on snow? Because that's a really important process going on. And for one, rainfall is increasing in mountain regions in the winter, and that leads to flooding, leads to greater avalanche risk. It leads to reduced snowpack longevity, things that we don't like as recreationists and researchers. And so I went, all right, let's see what goes on. But there was another objective as well. This guy, the Snowbro. In my first few months at the lab, there were about 5 different people that came up to me and said, oh, I swear the snow season is getting shorter and it's happening later in the winter. And the cool thing about being outside constantly, living in the mountains and being able to witness the stuff ourselves is that we do have anecdotal evidence. Sometimes it's way off base. Other times, not so much. but I thought, what's the harm of investigating it, right? So Snowbro was there to kind of help me guide science a little bit as a secondary objective. So the first thing we want to understand, of course, if we're looking at more rain coming in than snow, is what's happening to our surface temperatures. And these are average monthly temperatures from all the way back in 1971 through 2019 for both maximum, those red lines, and minimum daily temperatures. So if you think of the max and min for every day and average those, that's what I did to get this plot. And it's a little sciencey, I'm sorry, it's in Celsius, but the important bit is that 0 degree line, right? That's our freezing line. Because ideally, if our snow season is shortening, or if we're going to start seeing more rain, our minimum temperatures are going to be above that line. Now, these little dotted lines, those are our trend lines. And it's pretty clear to see where the trend's going in all of those. And this is data that we collected at the Central Sierra Snow Lab. So we can see what's going on with the trend lines, but if we're trying to figure out where the snowpack's going and what's going to happen to it, we want to calculate where this minimum line may cross that freezing line, because that means effectively that that month is no longer hospitable for snowpack, right? If we have snowfall and our minimum temperatures never get below freezing, it's not going to stick around. It's that simple. Maximum temperatures, it was a warm one today. It was 40 degrees up on top of the summit. That doesn't matter as much as long as we have good freezing temperatures at night. So when we calculate that out, we can see that 1981, 2006, October and May have already crossed those lines. They're no longer really hospitable for snowpack. And we saw that last year. We had 4 feet of snow fall at the Snow Lab last December, and all of it had melted by the first week in November. It was incredibly frustrating. And the same thing's happening with May. We're seeing these increases in temperature. Now, within 50 years, we expect to see November, January, and April follow the same trend. 100 years, March, and then 150, December and February. So that's what the past data has been telling us. I'm going to skip that a little bit. But after all, this is about rain and snow, right? So one of the cool things that we've done as researchers at the Snow Lab is we've taken and determined the total amount of precipitation, which includes rain and snow, and then just snowfall and snow water, which means we can separate rain and snow and figure out how much of each has fallen in every year and every month. So if you look at this, it looks a little busy, but basically the blue stars are snow, easy enough to remember, look like a snowflake, and the little green dots are rain. More blue stars at the top mean it's snowing more green stars at the top mean it's raining more for each month. And we can see that these trend lines are a little bit more muddied, right? They're not quite as clear. But if we do the same thing that we did with temperature, October and May have already crossed that line. We're already seeing more rain in those months than we used to. We're seeing rain as the dominant precipitation form instead of snow. So not all that surprising, especially when we get these massive atmospheric rivers that dump a ton of rain, and then we just catch a little bit of snow on the back end as things cool down. Within 20 years, we expect that to happen in November. So a lot of the ski areas, ski resorts in the area like to kind of count on Thanksgiving as their soft open, right? That's going to become problematic. That kind of already is without man-made snow, but it's going to become more so. Within 75 years, December, January, and April follow the same pattern. And within 100 years, we see March do the same. Now, February is kind of our outlier. It's a little crazy looking, right? We don't actually see much of a trend happening there. And that's because, at least hypothesized, it's been hypothesized that when we look at this in January, mid to late January, typically, there's a big high pressure system that builds off the coast of California. We get dry conditions, warm temperatures. In the past, that tends to break down before the end of the month of January and snow starts moving in again. But now it's amplified and we start to get more cold weather and snow moving in February. I'm not going into it in this talk, but there's actually a lot of upper atmosphere measurements that back this up, bizarrely enough. So that's some research that we're going to continue doing at the lab. But that's what's happening to our snow season. So we see on the edges, it is definitely shortening. And overall, if we look at what's going on, February and March will be the two with the most snow going forward, which matches what Snowbro was saying, right? later in the season and a shorter season. Yep.
Do you have any information about like the Alaskan current and the way that it affects the amount of the temperature of the water coming in and therefore the snow?
Can you repeat the question?
Yeah. Sorry. So the question was, do we have any information on the Alaska current and the sea surface temperatures and their impact on the snow? And the answer to that is kind of. So this last semester, I had a group of 3 undergraduate students working with me. They did a project, they're part of the data science program at UC Berkeley, and they were working specifically on whether we can determine snowfall amounts in the Sierra Nevada based off of the Arctic Oscillation, the Pacific Decadal Oscillation, and El Nino, La Nina, which are all sea surface temperatures, and which ones are most strongly correlated. Because as you guys, if you've looked at recent La Nina maps, we're always in that equal chances area where either we can get a lot of snow or very little. So we're working on really nailing down the relationships with that to determine what those sea temperatures mean for our snowfall. Does that answer your question? Ish.
Yeah.
Okay. Did you have more? Okay, we can come back to that. So that's what things are looking like. And the Central Sierra Rain Lab doesn't have the same ring to it. CSRL, it's not good. But as this is happening, of course, anybody who's been here during the summer too, that's not the only impact, right? We're not just seeing more rain, but we're seeing a lot more fire. We're seeing more severe fire. We're seeing greater areas of fire. And as we can see in this image from Williams et al. Just a couple of years ago, in plot C here in the Sierra Nevada, we are taking off in the amount of area burned. And I promise I'll bring this back to snow here in a minute. But when you look at this, this is really problematic compared to the rest of the state. Now, this is for a number of different reasons. Forest management is a big one. We haven't been managing our forest properly. I don't think anyone's going to disagree with that. But some of this is due to climate change too. And one of my biggest pet peeves when we talk about climate change and fires is that inevitably I get argued with about the fact that there isn't some climate change demon. Come on. Did we freeze? There we go. There's my climate change demon. There isn't some climate change demon literally going out there and lighting fires. There's always somebody going, yes, climate change isn't lighting the fires, it's people, or it's sparks, or it's whatever. And that's true. Climate change isn't some anthropomorphic demon that can go out there and start lighting fires. But what it can do is dry out our fuels. What it does is change our precipitation patterns to make sure our fuel loads are much higher than they ordinarily would be. And our forest health isn't as good as it would be, right? I don't think I'm, missing the point with this group. I'm sure we're all aware of that. But that's always one of my arguments that I get. Well, it's literally not lighting fires. Yes, we know. Thanks. So we'll get rid of angry climate change demon guy. He's out of here. But another thing that we're seeing, and this pertains to the rain as well, is that we have our wonderful atmospheric rivers. These produce the vast majority of our precipitation. We see our snow coming in big amounts like this last week. Last December, when we got nearly 18 feet on the summit, that was a lot of atmospheric river work, but we're seeing them warming as well. And Central Sierra, which is plot D down here, and I, for some reason, this is kind of weird. This is a paper that came out a couple of years ago and showed that we're actually getting warmer temperatures in our atmospheric rivers as well, which means we're getting more dense snow, which is good for water, but we're also getting more rain. So kind of a mixed bag, right? So all of this comes together to paint this rather ugly plot. I call it the plot of depression. This shows what's happening to our Sierra snowpack. This was a paper last year by Cyrilla Woodburn and another colleague of mine named Ben Hatchett, who's down at the Desert Research Institute. And this was published in Nature, so it has been vetted quite carefully. But effectively, if you look at this white line in the middle, that's our 10-year average in terms of the amount of area in the Sierra Nevada that will be low snow or no snow in the upcoming years. So on the right side of this bar, you see this nice blue area. That's where we want to be. We want to be close to 100% of what we call our snow water equivalent, or the amount of water in our snowpack. It's our bread and butter, right? You can see how much in the early portions of this plot that is out there. And we have this awesome 30 to 70 range where we might be a little bit below, but nothing terrible. But something awful kind of happens after 2025, which, by the way, guys, it's in 3 years. That accelerates dramatically. And the no and low snow areas that we see here really start to take over. With the current data we have by 2047, which is 25 years away, most of the Sierra Nevada will be low snow. By 2057, most will be no snow. Now, you'll notice we still do have a few areas, Peak Sweet is up here. And that's because, Hawaii gets snow occasionally. We're going to still have seasons. We'll still see snow come down on the highest peaks and things, but we're not going to have snowpack in the same way that we do now. So it paints a pretty bleak picture. It is the plot of depression. But as we have been discussing, rain and fire are a big part of what's happening, not just to our snow, but to our recreation as well. And these are actually research focuses of CSSL, which is another reason why I'm focusing on them a little bit. I don't know if I press on there. All right. So first, we'll talk about fire or burned forest effects on snowpack. And the reason why that's a fire/burned forest impact is because I said fire impacts on snow once, and people were really confused about how forest can simultaneously be covered in snow and on fire. So burned forest impact on snowpack. So ordinarily, if I'm at the university and I'm teaching this, now is about the time I have a really complicated schematic with an equation underneath it. I would like to tell you all, you don't have to worry about that. It's still in here, it's just hidden. So if you're a math person, find me afterwards. So these are some of the areas that I studied in Australia. And this one here on the right-hand side is the Caldor fire. Now, these are thermal images, and we can learn a lot just by looking at these. So these are temperature. Darker colors are colder, warmer temperatures are hotter. On the left-hand side, we have a living forest, and we can see these darker images on the ground where a shadow is cast as it blocks sunlight, right? We see this canopy up above. There's some goofy little kind of staticky looking things up there that are actually leaves, because the leaves in Australia the trees in Australia don't lose their leaves in the winter. And this is helping kind of mediate our snowpack temperatures and things like that. And it's helping keep us at a stage where the snowpack's quote unquote happy. It's not leaving early. We don't have melt. We don't have problems with it. This image in the middle is taken about 16 years after fire occurred. I should mention, for science nuts in here, these are not using the same color scale, so I would like to apologize about that. But what we can see here, this day was actually about 28 degrees Fahrenheit, and the temperature of those trees were about 60 degrees. So much, much warmer, right? Now, where this comes into play, you'll notice I don't have a schematic, but I do have goofy little icons in this right image. The reason that we're concerned is because even though we talk about temperature melting snow a lot, there was an unseasonably warm temperature pattern last winter, and that does happen. We are far more concerned about the sun. In the spring, it's not warm temperatures, it is the sun getting higher in the sky that melts our snow the fastest. So when we demolish a tree canopy, that becomes really problematic for our snowpack and for what we want to do to recreate in that area, because it affects the snow quality. The second thing that happens is you have less pine needles, you have less tree branches, and we're more exposed now, which means wind speeds are higher. And we have black tree trunks that are soaking up radiation and becoming hot. So that wind speed, the hot temperatures come together to create more evaporation, which means it's removing our snowpack completely off the hill, and we don't get the benefit of our water coming out of that snowpack at that point. Yep.
Pretty much the same at that, and you don't really have a good baseline data set for tree cut down Sierras.
Yeah, so the question was, oh, sorry. Thank you for reminding me. One of these times, yeah, but the question was, if we do the right thing and thin our forests or manage our forest, won't that create issue because you're removing trees that would be protecting the snowpack otherwise? And that's not necessarily incorrect. But forest and snow dynamics are incredibly, incredibly complicated. You know, there's a correct amount of thinning that you can do to maximize the amount of snow. There's also an incorrect amount of thinning that you can do that effectively removes more snow from the area that you're producing because it blows into the surrounding forest. There is a very complicated dynamic there. So to answer your question, yes, it would affect it, but if we're doing it in the proper ways, which are difficult to define because it often depends on tree species and location, then realistically, the benefits should cancel out any problems with increased sunlight. But that is very subjective and very complicated. There's been a lot of work. I can tell you that there's about 2 pages of my PhD solely devoted to talking about that. But John Pomeroy up in Canada, if you're interested in looking into that, did a ton of work on it. The Forest Service has done a ton of work on it. And the answer is it's kind of so complicated that we don't know if we should try. Because it takes a lot of manpower and there's no definitive way of doing it that always works out. So to answer your question, yes. But we've got this increased evaporation going on. The other thing too, you see our little fire symbol here on one of these trees. Of course, these are black. They're soaking up radiation. They're also dropping all that burned woody debris on the snow, which is helping it melt faster and also makes it harder for your skis and snowboards to glide over. Not too terribly, but it does. And in addition to this, we have issues with the soil. Fire changes the soil properties, which means you can get different lubrication with potential slides if it's on steep terrain. We see a lot of issues with trees themselves melting the snowpack. It kind of goes on and on. It's a big disturbance, right? I never know how often to click it. So what this results in are these 2 plots. And this is a model developed in Switzerland called Snowpack. And for those that know how to read snow and snowpack, grain crystals and snow pit charts, those symbols will mean something. For the rest of us, I will tell you that bright green is new snow. Darker green is snow that's kind of starting to change after it's fallen. It's starting to break a little bit. Our pink region is what we call rounded grains, which effectively is a denser snowpack. Red are what we call melt forms. So it's a portion of the snowpack that's already started to melt, but may not be actively melting to the point where it's completely leaving the hill. And then we have red and black stripes, which is a melt that then froze. There'll be a quiz later. No, so the point here is that the top one is in an undisturbed forest where fire never happened. It's pretty indicative of what we would expect a normal snowpack to be. We see different stratigraphy over the course of the year. When we look at after a fire's happened, we go right from, hey, look, no snow, new snow, to, oh, it's melting. We don't have the same type of setup that we do in an ordinary forest. And that, again, poses issues, especially when you're trying to avoid things like maybe trees that have fallen over because your snowpack melts a lot faster and reveals those hazards versus in an undisturbed forest where it's going to stick around more and be deeper. So this is a little bit more that we're looking at, and I'm going to briefly glance over these, but if you can imagine taking a meter stick this is America, yardstick, and put temperature sensors on it, that's effectively what we did when we were measuring snowpack temperatures vertically. So this is from the ground up to the atmosphere. That top one on the left, well, there's only one plot. The top one is air temperature. The bottom 2 are the snowpack temperatures that respond. So the first thing you'll immediately notice is that our snowpack in the undisturbed forest is deeper, right? It's about 60 centimeters, so about 2 feet. In the fire disturbed forest, it's about a foot less than that. Now, we've already established there's faster melt. There's a little bit less snow depending on where you're looking at it. But the other thing you'll notice is that it responds a lot faster to changes in temperature. So we have a lot of the changes in temperature that only affect the uppermost parts of the snowpack. And then in the fire disturbed forest, that goes all the way to the bottom because of how much shallower it is. So this really drives home the point that the conditions in those areas when we go out into them are increasingly variable. They depend so heavily on what's happening that specific day versus where we can assume kind of a homeostasis or a more managed snowpack in an undisturbed forest. This is very much the same thing as the left plot, but we looked at temperatures around tree trunks. So we stuck thermocouple, what we call thermocouple ladders, so just temperature measurements on sticks, basically, north, south, east, west, to figure out what's going on with temperatures around tree trunks, which are in the middle of these little circles. You'll notice that the east measurements are suspiciously gone from both. We had what we call an unplanned animal interaction with one of them. I'm fairly certain, even though it was cute, a wombat knocked one of them over because this was in Australia. And the other one, I'm not sure what happened to it, but something similar. So luckily it happened to both of them. So I didn't have to worry about only dealing with one set of data on the east side. But basically, these are average temperatures around what you might assume to be a standard tree trunk in a forest. In the living forest, which is up top, we have 2-hour increments from basically midnight all the way through 10 p.m. In local time. You can see that we have this dark color, which is a colder temperature, develop around the tree, and then slowly kind of work its way out to warmer temperatures later in the day around 18, 20, which is 6, 8 p.m. On the bottom, on the other hand, we have this dark, colder temperature around the tree trunk that develops because of a tree well. This is all tree well based, right? And then as soon as we hit 10, we have this bright flash of warm temperature on the north side. Now, remember, southern hemisphere Australia, north side is where the sun's coming from. So we have this bright flash of temperature that is bringing more heat into the snowpack that continues throughout the day. So when we looked at this with other meteorological parameters, we realized that realistically, living trees and the tree wells around them help cool down our snowpack, while burned trees do the opposite. Now that seems pretty standard, but the weird thing is it doesn't just happen at the surface, it goes all the way down to the ground as long as there's a tree well around it. Yep. So the question was, do I have any data that differentiates between deciduous trees and conifers? And the answer is not yet. This was all done with eucalypt trees because, what's that? They don't drop leaves. So the eucalypt trees, they're called snow gums or Eucalyptus passiflora. They don't drop their leaves in the winter, which makes them really good at catching snow because it slows down the wind and it filters into the forest. But we haven't had the chance to do this really up here yet. That's on my to-do list. That's kind of been pushed aside because I've had other laboratory duties recently. But I'm very excited to do this experiment and would love to do it down in the Calder Burn Scar or the Dixie Scar or some of these areas, because I think it would be really fascinating to see how it compares up here.
Can I ask you a question from the line?
Yes.
How do you define undisturbed forests? Most of our forests have been disturbed by man. Any sense of what happens to thin treated forests?
Okay, do you need me to repeat that one?
Sure.
Okay, so the question was, how do you define undisturbed forest? Most of our forests have been disturbed by man. And what was the last bit?
Any sense of what happens in thin treated forests?
Any sense of what happens in thin treated forest. So disturbed forest in this case is just one that's been impacted by a fire. This, the reason why this is a little bit different is because we said burned versus non-burned, and it caused a figurative fire amongst our reviewers that said, well, just because a forest is burned doesn't mean it's dead. And just because it's, it's basically, there was a lot of semantics, and we said, can we all settle on undisturbed being the one that didn't burn and fire disturbed being the one that did? And we all went, yes, okay, cool. And so that's how the paper was published. So that's why that wording is a little bit weird. To answer the question, yes, most forests have been disturbed in one way or another, especially as we live in ski country. A lot of them have been changed for ski courses, things of that nature. And without getting into the specifics of each forest, it's hard to determine what specific impacts there are. Down in Australia, if I recall correctly, it's actually a federal crime to cut down a snow gum, which is what the study was done on, because they are a protected species that are being threatened by snow levels moving upward because they love their cold temperatures. So any disturbance is pretty far in the past by at least several decades at this point. So they're starting to return to more so of a homeostasis, but that's not the case up here necessarily. So was the question answered sufficiently, I suppose? We'll say it was. I think I did a great job. So we can come back to that if somebody disagrees. Cool. So this starts my frustrating. Nope. Too far on that. Back one, maybe if it wants to. I don't know what it's doing. Cool. Thank you. Got excited and then it broke. All right. So all of this fire talk, it does impact how we go outside, and I'll get more into that in a minute. But the frustrating thing about it is we develop a feedback loop. And for some reason, when I created this, I put kind of like the beginning at the bottom. I'm not sure why. So apologies for that. It was just terrible. Andrew was not smart. But we kind of have these severe wildfires that start, and then as a result of the processes that we just talked about, reduce the snowpack in the areas that we want to be in, right? So it makes it more difficult for us to go out in these places. It also makes it more difficult for us to develop runoff, which means we have less stream flows and storage, and then we have more drought, especially because when we have less stream flow, our ecosystems aren't as healthy, puts them in a state of stress. And then we end up with drier soil and fuels, which then leads to more severe fires. So this is one of the reasons why we're focusing on this. When we talk about mountain ranges, like the Rocky Mountains, like the Sierra Nevada, like the Snowies down in Australia, this is the kind of cycle that we're developing and one that we need to get out of. And as I mentioned, some of this is climate change driven, which means it's going to be really hard. Some of this is forage management, which means hopefully we can address it a little bit more. All right. So as far as the hazards associated with this, I've mentioned a little bit of them, but of course, we're all aware of what happens to dead burned trees. We've got several that have already broken here on the right-hand side. We've got several that are leaning into the forest. These images, by the way, were taken by the very wonderful Marion Cowherd. She's a PhD student at the University of California, Berkeley. I've worked closely with her on developing her research, which is studying the Calder fire and the snowpack in that area. So you'll notice, look at how wonderful, she's got high vis on, she's got a helmet, A+ for safety in the backcountry. So Marion was hiking around. Of course, we're well aware that these trees fall over pretty quick after the fire. On that right image, that's what we call a severe burn. So no real pine needles left, lost a lot of the branches, things are already falling over. Now, one of the trickier bits about this is if you look at the left image that I'm walking in front of when I say that, there's still pine needles on those trees. Those trees still look alive, right? But we've seen in research that even moderate burn areas like this, those trees can die within the next 1 to 2 years and will become a hazard, right? So these may look healthy for the time being, but they can die very quickly and become just as much of a hazard as the ones in the right image that are prone to falling over. Okay. So that leads to this type of scenario, right? This wonderful picture by Monica Ruther. But those trees, regardless of how long ago that fire came through that area, are widow makers and fool killers. And those are not my terms, those are forestry terms. But they're ready to come down on you at any given time if you're moving through that area, right? And that needs to be brought into account. That's why Marion was wearing that helmet. Probably not why she was wearing the high vis, although it would be easier to point and laugh at her on the ground if a tree branch hit her in the head, right? There you are. But they also pose an issue for being buried in the snowpack. Like I mentioned, we get less and less snowpack in these areas because of how quickly they melt. And when you have a bunch of these tree branches, tree limbs, tree trunks sitting underneath the snowpack, they pose a serious issue if we are going over the top of them and not knowing. Only 2 weeks ago, somebody at one of the local resorts hit a partially buried tree and broke their back in 3 different places. So when we talk about backcountry safety, knowing where objects are in the snowpack is a huge one. Or just knowing that they're there and moderating your speed, right? Happened inbounds. So in addition to this area and these hazards, we also see greater variation in weather conditions, right? We have those trees warming the area during the day. We have higher wind. And then as soon as the sun goes down, we lose those warmer temperatures and we get a big temperature swing, and we can get big winds as a result of that temperature swing as well. So we end up with more variable weather conditions that you have to plan for when going out into these areas. And then also of course, when you're in a forest that looks like this, not really many places to get out of the elements, right? Increased exposure is a problem as well. I don't know why I keep coming over here. Get my steps in for the day. So on terrain impact on snow. Maybe. There we go. So if you can all describe to me this plot on the left. No. So basically the important thing about this plot on the left is the very top bit. And that's that blue line is how much rain was coming in, or the rate of rain roughly. And then the red line is temperature. And you'll see that this event that happened in Australia was associated with an atmospheric river that warmed right as the heaviest rain amounts and precipitation amounts were hitting. And that happens frequently up here. We often get a lot of warming that happens right as the heaviest amounts are hitting. And that leads to things like we see on the left from Ben Hatchett's paper in 2018. We have flooding, we have slides, we have landslides. Sorry, snow slides, avalanches, and landslides. Although I think technically in that meadow, it's just more so flooding than an avalanche. And that's the problem, right? We see these big dumps of rain and they greatly affect our snowpack, and we get all these responses in return. And if you're in those areas, then it can create a significant issue. Yep.
Is that due to like the symmetric angle at which the atmospheric river is coming from, or does it have to do more with some sort of effect that needs to mediate I don't understand this. What part of the one that comes to
Yeah, so I mean, you can see it doesn't jump right before it, like we kind of build up to it. But this kind of goes into what we call mid-latitude cyclone dynamics. So if you're really good at differential equations and linear algebra, it's for you. Look it up. You'll enjoy it. But basically, oh yeah, sorry. So the question was, is there a reason specifically why we see this jump in temperature as the heaviest parts of the storm come in? A lot of that comes down to geography. Some of it comes down to the way that mid-latitude cyclones are arranged. So if you pretend you're staring at a low pressure system on there, there's a warm front that's typically connected to the cold front. And along the coast, those aren't very well separated. And typically the cold front's actually chasing warmer air out ahead of it. So as we get what we call cata fronts, which means the precipitations on the front, they're often encountered with warm temperatures that then fade after the front passes and get colder again to bring us snow. That's one of the reasons why we see it out here the way that we do, and in maritime areas the way that we do. It gets into really fascinating weather dynamics, basically, but probably a little bit advanced for what we're talking about here. But that's realistically why we see that jump a lot of the time. We do see, so this is what we call a right side up storm. We start warm, and then as we get cold air moving in behind the cold front, it cools down. We do have things called upside down storms, where we start cold with snow and then rain falls on top of all that new snow. And that's a problem that we see out here. And I'm sure you guys are not fond of those either, because you're like, yay, snow. Oh, it's ruined. I know, I've been there. So this more often than not, we see the right side up storms, right? Cool. So these lead to issues. And the fortunate things about rain on snow is it's very easy to diagnose, even if you weren't there when it was falling. On the left-hand side, we see indications of what are called preferential flow patterns in the snowpack. And it's just those squiggly little snake-looking lines. So basically, as rain falls, oh, those did not translate well at all. As rain falls on the snowpack, we get these little areas where it wants to travel. It'll either hit a hard layer and move horizontally, or it'll find an opening in that layer and percolate downward. Now, anywhere where that water is moving in the snowpack and finds one of those hard layers and starts to move along it, you find these little fun patterns in the left image. That was taken at the Snow Lab last year after a rain event. So those kind of patterns are really indicative that rain has fallen on that snowpack. And that leads to a couple different things. For one, lubrication of the layer on top of the ice layer that can lead to slides. And we can see that over here. We have an ice crust, we have a nice big layer on top of it, and we see infiltration of free water through the snow that will cause lubrication of that top layer. And that's problematic. Also, if you guys don't have the Avalanche Handbook by, what is it, McClung and Scherer, you should definitely get it. It's a terrific book. There we go. So this ends up leading to what we call wet snow or slab avalanches, where effectively we get a lot of rain, which, as I mentioned before, is increasing in most of our climates. We're seeing more rain on snow, right? So we get added load, we get added weight to our snowpack because water weighs a lot more than snow does. And as a result, we see slides that develop. Now, that additional load can occasionally be enough to just trigger a slide. Sometimes, if it does hit an ice layer, it'll develop lubrication as well, and that's important too. But overall, it becomes an issue. So that's, of course, going into the backcountry in the winter, a big concern, right? Our avalanches. The other thing too is the Oroville Dam disaster. That was a rain on snow event. We get massive flash flooding in the right conditions. And one of the things that's interesting about rain on snow is that we don't know that much about it. There's a lot of, this is one of, do you have a question? Yeah, what's up?
Does the weakness caused by the rain on snow ever stabilize, or is it just like we've had rain on snow here last week?
Yeah.
Does that mean it's going to be bad all winter? Does it mean at some point it freezes enough where it stabilizes?
So the question was, basically, if there's a rain on snow event, is there potential danger all winter, or does it stabilize a little bit after it refreezes? Realistically speaking, you can get slides up to 3 days after these events. After that, it starts to diminish in terms of likelihood because it does refreeze. You start to get more stability in the snowpack, and rain actually under the right conditions can help congeal the snowpack too. So realistically, I would say the first 72 hours after an event, that's when you're most likely to see that loading, because after that, that rain or free water will percolate down through the snowpack and either exit or it'll refreeze and become a solid layer. So this is one of those areas where we don't know a ton about in terms of snow. And that's hard to believe considering we've been researching it since 1878, basically. There is some type of threshold, and we don't know what it is, that either one will let water flow through the snowpack freely and then go downhill into our streams, or two, melt the entire snowpack and cause massive amounts of flash flooding. And we don't know what that threshold is yet. There's a lot of people at the lab working with me on it in terms of collaborators from the University of Nevada, Reno. Adrian Harpold is a really good person that's studying this right now. But there's a number of us around the world that are trying to determine where that threshold is, because if we can figure it out, then flooding in Reno, flooding out in Meadows, that can be forecasted better than going, it's going to rain. We're not quite sure what's going to happen yet, So that's a cutting area of research. But anyway, so Oroville was a result of rain on snow. If you were caught in the backcountry during that, it was probably a really bad time to be out there. And then, of course, we have landslides as well. Just as we're lubricating that snowpack on top of the slopes, we're lubricating the soil on them as well. And we can get slides that develop in those areas when we get rain on snow. Hazards and snow loss action. Things that you can do at home. Cool. So I heard this for like the 40th time this last week. Ego is not your amigo. Jeremy is an awesome person to go listen to talk to. Local. Woo. But ego is not your amigo, right? Like when we're going out into the backcountry, first things first, you want to make sure that you're identifying your recreation locations and keeping an eye on them as close as you can before you're going out there. Identify the hazards before they're covered up with snow, if you can. That's not always possible. But the second thing here is we're talking a lot about exposure. We're talking a lot about rain. keeping an eye on the weather forecast and the snowpack conditions. If you have upcoming rain on snow, probably not the best time to go out on steep slopes. If you had it in 2 days prior to when you're planning on going out, again, rethinking things. And then as we're looking at the places we want to go recreate, just identifying these hazards. And the ego is not your amigo thing really comes into play when you're out in the field, right? Despite wanting to be on this trip and do as much as you can on this trip, if the conditions are not there, if there are hazards that you weren't anticipating, reacting to those is the most important bit. So if you see an area that's burned and you're starting to notice a lot of logs poking up, maybe wait for another storm. If you're seeing another sign of our snowpack with water in it, which is the bottom right-hand slide here where you can see these kind of dots on it, that's a sign of rain on snow too. And you haven't been in that area, you don't know when that occurred, it's time to be cautious. Yes, you might be experienced, but those are the times when you can really second guess things, maybe dig a pit to see what the stability is like. That's when you really want to be cautious. And of course, have proper equipment for the locations. If you're super stoked to go into the backcountry, into these areas that have been burned, bring a helmet. It might not be the full tree. If a full tree falls on you, I don't know if a helmet will save you, but if a tree branch does, it certainly will. So have the right equipment with you always when you're out in these areas. I'm probably preaching to the choir on that one a little bit. And then finally, in terms of curbing our snow loss, vote. Okay, so I have a dirty secret, and that's who's used a carbon footprint calculator in here? That was a marketing campaign by British Petroleum to take the emphasis off of them and put it onto you. Ignore those carbon calculators if you can. I still use them because I like to reduce my carbon footprint, but realistically, the more impactful thing is getting involved with legislation and voting. So vote, find your local politician and take them out to have fun with you if you're John Muir, or do things like joining Team POW. I mentioned Jeremy earlier, Protect Our Winners and the Save Our Snow campaign here. Terrific ways to get involved and make sure that we're making large scale adjustments to combat our snow loss. Because individual actions are awesome, but until we pull ourselves away from the big scale fossil fuels, we're just not going to make enough of a difference. And if Jeremy were here, he would tell you how the IRA this last year passing the Inflation Reduction Act was amazing. The largest climate bill in world history that will force other nations to follow. Absolutely awesome, which is why within Protect Our Winners, I am a Science Alliance member of Protect Our Winners. We call it the BFD, or the big deal, because it is such an amazing bill. But that's what we need more of. And so if you want to help curb our snow loss, if you want to help curb a lot of the, the plot of depression that I showed earlier, get out and get involved with your local politicians, legislations, and vote in every single election. And I think now that I can step off my soapbox, that's it. Open it to, and on that note, go back. Yes. If you're interested in Save Our Snow and getting more involved and making more of a difference, go to the back of the room. There's a board in the back left-hand side. Everybody look that way and point. This is interactive period. Go back there, scan the QR code on that board, and that'll take you to how you can really start getting involved and making a difference with our snowpack and everything. Yeah, question. Oh.
Yeah, I know there's, general sense of CO2. However, the temperature seems to fight it down nationally or worldwide. And the last 7 years have actually been cooling nationwide. California is different. What do you think of the other theories out there, like from the astrophysicists who are looking at the magnetic dipole of the sun, Valentina, Darkova, or folks like Henrik Svensmark, who's done quite a bit of work proving that there is a relationship between cosmic rays and cloud nucleation, and that clouds are the primary driver of temperature and precipitation.
Okay, so the question was, the agreed upon consensus is that CO2 is producing climate change, and asking my opinion on things like the pull of the sun and our solar cycles, as well as things like cloud nucleation and clouds being the dominant control on climate cycles, especially because we've seen a short period of cooling in parts of the United States. And I'm going to be really gentle when I say they're all wrong. Any chemist can tell you that carbon dioxide holds a lot more heat than the other gases that are in our atmosphere. So increasing that concentration will warm the atmosphere. And it's not just carbon dioxide, it's methane as well. As we get methane emissions that are pouring out as a result of our permafrost thawing, and as we're releasing those from the production of fossil fuels, methane is so much more potent than carbon dioxide. And guess what? It breaks down to carbon dioxide eventually, which means it's contributing more. So those theories, they're nice. I appreciate them. I've looked into them, but unequivocally, it is really, really what we are doing with our emissions. And that's quite evident when you look at just how severe the arc is as soon as we hit the Industrial Revolution, to be completely honest. Other questions? Thoughts? Yes.
So I was at a super computing conference a couple weeks ago, and one of the interesting topics in the climate modelers was there was that massive volcanic eruption in the southern hemisphere, and it introduced a notable amount of water in the southern stratosphere. And they were saying that was starting to draw heat out of the tropical areas, shifting the band of the tropical heat south. And I specifically asked them about what, because of the La Nina thing, and we're right on the edge, how they would say, and the answer I got from them was, oh, well, that event is entirely unprecedented. We don't have any data on this. We're really interested in watching it. Have you picked up any signals from that in any data you've gathered yet, in terms of the geometry of the tropical of the mid-latitude cyclone?
Yeah, so the question was, I think you're referring to the Tonga eruption, is that correct? So yeah, so the Tonga volcanic eruption that happened this last year ejected massive amounts of water vapor into the troposphere, which is the bottom portion of the atmosphere, and even the stratosphere. So the question was, have I seen any signals of that in what we're doing in terms of the mid-latitude cyclones? And honestly, I think it's too early to tell. With those types of massive disruptions, what we typically do is something called an attribution study. And when you hear scientists or atmospheric scientists, meteorologists, whoever say, this event was worse because of climate change, you go, and I'll admit I do the same thing. I go, kind of. But attribution studies of one of the ways that we actually tell what could be versus what is, in terms of if we had a normal atmosphere versus what is currently happening. So through these studies, we can back out the signal of climate change in each individual event through specific modeling practices, through specific analysis practices, and we should be able to do the same thing with the Tonga eruption. That being said, with any type of large scale alteration of the atmosphere, we see significant lag times. So it might be a while before we can get around to figuring out what that is. With climate change, our emissions from today, we won't be able to tell what those impacts are for another 15 to 20 years, which is the really fun bit, right? Because if we stop right now, we're still in for some really exciting stuff. But it's not, those large eruptions aren't unprecedented. Krakatoa released a massive amount of particulate in the atmosphere that actually cooled us for several years after it erupted. The interesting part about this one, though, was because it was at sea level, it ejected water rather than specific little pieces of volcanic rock and ash in the atmosphere.
Injected into the stratosphere, where you don't have a lot of water.
Yeah. The point was that it was so big that it ejected it in the stratosphere, and that's completely correct. And most atmospheric scientists, meteorologists, we deal with troposphere downward. I'm very well aware of how the stratosphere works, but there's all kinds of weird physicsisms with the stratosphere that I'm not as well versed on as other people are. So I can speculate as to what could happen, but I'd rather not, just for sake of accuracy, to be honest. Other questions? Favorite foods? Favorite mountains? All right. Sugar Bowl. All right. Yeah, I'll agree with that one for sure. Cool. Well, thank you guys very, very much. I'll be hanging out for a little bit. And if you have any questions or want to chat, feel free to come up and accost me.